Hello again. We're going to resume our discussion of feature engineering. In the last lecture, we reviewed that many times our raw data is not in a form such as a feature matrix. It might be images or audio or text, or it could simply be time series data that we want to summarize in some kind of way, or any other number of things, in which, in order to create a data set that we can actually pass to a machine learning model, we first need to extract certain features. So we considered an example in which we looked at the autocorrelation of surface temperatures in different cities around the world over the course of a year. And we found that the 6-month autocorrelation could be a good discriminating factor between different cities, or different latitudes more specifically. And if we were to plot this new feature that we had constructed against latitude, we found a very strong trend. So all these cities appeared to fall along some kind of nicely behaved curve. But this is clearly curved. It's not linear data. And that limits, to some degree, the sorts of models we could fit to this data. We also considered another example, this California housing data set, in which there was geographic features that clearly contained meaningful and predictive information, but needed to be transformed in some way so that we could extract the relevant feature. In the case of the temperature data, we considered what kind of shape this curve might have. If we were trying to fit a line to it, we can see it does a very poor job because it consistently overestimates in this region while underestimating in the tails. And I looked at this and I said, this looks sort of like exponential decay. It's decreasing sort of quickly here and then levels out to a flat region. And we transformed the data using that exponential formula. And this transformed data looks fairly linear. So we could fit a line to it and then use this mathematical transformation in reverse to make predictions. And we saw that it gave us this nice, smoothly decreasing curve that appears to capture the trend in the data while avoiding some of the noise of a higher variance model like a decision tree. And in fact, it even performed slightly better than a decision tree. This exponential model had a lower mean squared error than our decision tree. So these introduce the idea of feature extraction and feature transformation, where we might be adding features to our data set or changing features in some way to make the data more available to whatever model we choose, or to tease out the latent information in the data. Now, often adding features in this way can help us investigate trends. It can help us discriminate between different classes or regions of our data. But adding features is not always helpful. So let's address this issue. When is adding features a good idea? So first, let's consider the case of how adding features helps. So here we have a data set with just one feature, one measurement. So each data point lies somewhere along this line. And I've made two histograms. So some of these data points belong to a class colored in orange, and some of them belong to a class colored blue. And we can discriminate between orange and blue using the measurements. The orange data points are centered further to the right than the blue data points. But there's a fair region of overlap here, where if I draw a point, say at 1 or 1/2, I can't be very confident that that data point is orange or blue, because in this region from 0 to 2, the orange and blue classes overlap quite a lot. It's possible that by measuring some additional feature, I might be able to further separate these two classes. So if we add another measurement, imagine that we go out and these could be measurements of the height of some plants, two different crops, and I want to know if I'm dealing with one or the other species of bean plant. So maybe there's some blue bean plants and some orange bean plants, and the orange bean plants are somewhat taller than the blue bean plants. Well, maybe I also go and decide to measure the width of the leaves on the bean plant, or the length of the beans. I make some new measurement. And now, my data exists in a two-dimensional feature space. I have the one dimension that I had before, the height of the plant, and now I have an additional dimension, the width of the leaf. And now I can see that there is actually a little bit less overlap. These two regions are now more distinct, because if I look from 0 to 2, where I was looking before, where they overlap, if I am up here at 3 for the width of the leaf, I can be pretty confident that this is in this orange or red class. On the other hand, if I'm down at 1, but I'm at -1 for the width of the leaf, so maybe these have had the mean value subtracted off. These could be z-scores or something. Here, I'm pretty confident that I'm blue. It's only when I get into this region, from like maybe 1/2 to 1 or 1.5, and additionally narrowly around 1 here, that there seems to be significant overlap between the two classes. So the region of space where there is much overlap is now narrower because there's more dimensions along which these two classes can differ. One way to think about this is if I was trying to train a linear model to separate these two classes, what kind of line would I want to draw? I would want to draw a line from the upper left to the lower right, passing through this region of overlap. and it would be perpendicular to a line connecting the centers of the clusters. So that would most cleanly separate them. However, if I only had one dimension available to me for measurements, I could only draw a line separating them at a particular position along this axis. So when I had one measurement before, I might draw a line here at 1, separating the two classes. And that way, whenever I make a prediction, if I'm to the right of 1, I predict orange, and if I'm to the left of 1, I predict blue. So that would be like drawing a vertical line here. But I can do quite a bit better by drawing this diagonal line. So we can consider training two models, one on the full two-dimensional data. So this is a logistic regressor, which will exactly calculate this line of separation between the two classes. And this one works in 2D with the full data set. This logistic regressor works in one dimension with just the first column of the data set, just this axis along the bottom. And we see that the logistic regressor that was trained on the two-dimensional data more accurately predicts which class new data points belong to than the logistic regressor trained on just the one-dimensional data. And here's a visualization of what these two logistic regressors are doing. The one-dimensional logistic regressor can only draw a vertical line somewhere along this axis. And it chose to draw it here. And we see quite a bit of red points fall to the left where this one-dimensional logistic regressor would be predicting blue. And likewise, to the right of it, where it would be predicting red, quite a few points are blue. The two-dimensional logistic regressor draws this diagonal line through the plane and more cleanly separates the two clusters. So I've shaded the prediction regions red and blue for the two-dimensional logistic regressor, and we see there's very few red points in the blue region and very few blue points in the red region. So this illustrates how adding more features can potentially help us. But how can adding more features hurt us? This is difficult to think about, and it's difficult to explain because I can't make visualizations very easily in 3 dimensions, and I can't make any visualizations in more than 3 dimensions. But the story goes like this. If I have some data, so we'll start with 1,000 data points. And what I'm going to do is add a little bit of noise to them, but I'm going to have so I'll make a scatter plot with some data. And imagine, we're looking at a signal that looks like this. So there's some noise but I can see clearly this is a sine wave. Even if I increase the noise quite substantially, I can still clearly see this sinusoidal oscillation. This trend looks like a sine wave. I also know it's true because that's encoded in the way that I generated the data. But even if I increase the noise quite a lot, I can still see this trend. And a big part of the reason is because I have so many points. The points give me collectively outline this trend. Let's take away some of the points. So I'll decrease the amount of points by a factor of 10. Now it's not too clear that this is a sine wave. I can sort of see it, but this could also be, say, a downward facing parabola. It's not obvious that it's increasing again over here. And if I decrease the number of points again by a factor of 10, now I have no idea what kind of curve these points are supposed to be outlining. If I have less noise, then I need less points to see my trend. So here, with less noise, I've turned the noise down to 0.1. After having 25 points, I can start to see this sinusoidal pattern emerge. And as I increase back up to 100, I start to become pretty certain that this is a sinusoid. So there's a trade-off between the amount of variance and the number of points we need in order to detect some signal through the variance in our data. Each time we add a new dimension to our data, each time we add a new feature, we're going to introduce some variance in our data along this new dimension. So in our example here, initially we had one feature, the height of the bean plant. And there's some variance, some random differences between the different plants regarding their height. If I additionally measure the size of their leaves, there's going to be some variance in the size of their leaves. And so my data gets spread out not only along X, but also along Y. Now, the reason that adding the size of the leaves as a feature in this case helps us is because not only are the red plants taller, they're further to the right for the height of the plant, but also the leaves are bigger. So the centers of these two clusters are not only separated in X, but also, or not only separated by the height of the plant, but also by the size of their leaves. But if they weren't additionally separated by the size of their leaves, this new information wouldn't help me at all. And in fact, it can begin to hurt me because my data points are getting spread out along this new axis. And if I keep adding more and more dimensions, there are more and more directions along which random fluctuations can occur. And so my data will start getting spread out in more and more directions. And as my data gets spread out, it starts to become sparse, meaning I start to have not enough data points to be able to detect the underlying trend. And this problem is even worse if my variance is quite high. So by adding new features, I'm adding variance to my data and spreading them out along new directions. If that new feature also adds useful information because there is some trend in that new feature, then that can be valuable. But if it doesn't have a strong trend, then the variance introduced by this new feature only serves to make my data more noisy and decrease sort of the signal to noise ratio in my data. This problem is known as the curse of dimensionality. You can read more about it, not only on Wikipedia, but there's YouTube videos and many other places where this is written about. It's a bit hard, it's a difficult concept to understand, partly because it involves thinking about how these points will behave in high dimensional spaces, 4-dimensional space, 5-dimensional space. As we add more and more features, for instance here, these points can get spread out over more and more dimensions. So we could have not just the size of the leaf, but also the length of the beam. And then we would have a third dimension, maybe coming out of the screen. And then we could also have the color of the flower or something like that. And we would have a fourth dimension that this could vary over. And so thinking about what will happen to the points as I increase the size of my space, the dimensionality of my space, is a little bit difficult. But at the very least, hopefully you're able to follow this idea that it will get spread out over these dimensions. And when it gets spread out and sparse, like I've illustrated here, it can become difficult to detect any trend through the noise. So if we don't want to always keep adding features, maybe we want to be careful about which features we actually use and keep around when we're training our models. So for example, in the previous lecture, when we were looking at the California housing data, I showed this plot that showed that the average age of houses has no relationship with the average price of houses in a given neighborhood. This is just random scatter. It's totally useless for predicting house price. So maybe I shouldn't keep that feature. It might just be adding noise to my data. And maybe I could simply get rid of it, and my model wouldn't suffer for it, and my model could even potentially improve. because it won't be incorporating the variance into the model. We might reduce the variance of the model by eliminating this extraneous feature. So there are many ways to assess feature importance. I'll show you one here. So we're going to train a decision tree on all of the California housing data set that I showed earlier. So here we're splitting up the data set into a training and a test portion. We'll scale it, and we'll fit a decision tree regressor with the training data. I'm also going to use this randomized search CV. You've probably seen grid search. This might be the first time we've introduced randomized search, I'm not sure. It works very similar to grid search, except instead of providing particular values to test for the hyperparameters, we're going to randomly choose certain hyperparameters from the space described by the grid in grid search. So rather than systematically working through the grid, we'll just randomly pick out points in the grid. And this can let us sample a larger variety of hyperparameters. So we'll try 200 random combinations of max depths between 1 and 9. And we'll try min sample splits between 1 and 90. So this will take a moment to train. So our fitted model achieves an R squared on the test set of nearly 66.66. So our trained model explains roughly 66% of the variance in house prices. We can examine the feature importances in the model by using the feature importances attribute. So decision trees have a feature importance attribute. If you look at the scikit-learn documentation, there's a list of attributes of the decision tree regressor, and feature importances is one of the first ones. And it tells us the higher the score, the more important the feature is. So if we sort this, oh no, not what I meant to do. I apologize, we'll have to wait another minute while this trains again. Here we go. So the most important feature was that median income, which we saw earlier had a strong linear relationship. And many of our features were not so important. So median income had a feature importance score of 0.7, whereas house age, the random one that I said wouldn't help us at all, had a score of 0.046. And surprisingly, at least I am surprised, some of these other features had even lower importances in our trained model. Another way to examine feature importances for linear models is based on their coefficients. So a decision tree is a nonlinear model, but it happens to have this feature importances attribute. And these importances are calculated in relation to how decision trees choose how to split up the data based on the various measurements. So this is also called Gini importance, which is related to the Gini coefficient or Gini impurity, which is used in the algorithm for training decision trees. And you can read much more about that in the scikit-learn documentation. There's a user guide where the algorithms used for making splits in a decision tree are described. For linear models, we know that when two variables are correlated, that means they are dependent upon one another. If they're uncorrelated, if the slope is 0, then as some feature varies, it has no effect on the output. So simply by looking at the coefficients of a linear model, we can also get an estimate of feature importance. So here we train a linear model to the same data. Much of our data is nonlinear, so the R squared is unsurprisingly a bit lower. But the story about feature importance is pretty similar. So median income was one of the most important variables. Surprisingly here, latitude and longitude both got picked out as important by a linear model, despite the fact that they are clearly non-linearly related. Meanwhile, house age and some other variables are down here at the bottom. Why don't we try this experiment briefly with the feature we constructed earlier. So I'm going to replace latitude, longitude with our dist to city feature. And if we train this again, Oh. There we go. Well, to my surprise, our distance to city feature ended up not being very helpful for this linear model. To me, it looked pretty good, but that's the way it goes sometimes. We could try removing some of these less important features and seeing if they help us actually make a better model. So, for example, so I've reloaded the California housing dataset, so we're back to the normal features. But here, where we create our training and test sets, I'm going to drop some columns. So I'm going to drop house age, since we know that one doesn't really help us. So I don't quite recall what our R-squared was earlier. I think it was just under 66%. Of course, each time we split up our data differently, we're going to get somewhat different scores, simply because our training set and our test set are slightly different each time. But it is worth noting that dropping house age basically didn't hurt our score at all. And possibly it even helped. And it also has the added benefit of making our model simpler. House age doesn't meaningfully contribute to the model, and by removing it as a feature, we explicitly are saying that this is not a factor in how we make our predictions. And our model becomes simpler and more explainable, which can also be advantageous in business or academic settings, where you are trying to communicate what your algorithm is doing to others. Scikit-learn also provides some tools for removing features that may not be helpful. So the documentation has a whole section on feature selection. So there's some like select K best, remove all but the K highest scoring features. Select percentile, where you select features based on them contributing within a particular percentile to the evaluation metric. We are going to briefly demonstrate this one here, recursive feature elimination, where we try eliminating features one after another and determining their impact on our evaluation metric. Because not all models are so easily interpretable that we can just print out the feature importances or the coefficients and know which features are most important. In some cases, we need to actually train with or without various features and look at their impact on our evaluation metric for our model. So this recursive feature elimination cross-validation object is going to automatically eliminate features one by one, fit the model, and then calculate the evaluation metric with the fitted model, and then report back to us which features made the biggest difference. So as we can start with just one feature, and as we build up more and more features, we start to perform better and better. But eventually, adding more features doesn't help us and may in fact hurt our predictive capability. It looks like there's a slight decrease from 4 to 7 through here. Certainly it's at least flat, but it might even be getting worse. So this recursive feature elimination is telling us that we might not want to keep all the features in the housing data set, because that we might be suffering a bit from the curse of dimensionality. And we might not, these extra features might not be helping us in any way, and could be, dimensions along which our data is simply becoming spread out. Another technique for dealing with overfitting, particularly from high dimensional data, is regularization. So I've mentioned the evaluation metric several times. It's a quantity that we compute to evaluate how well our model is performing. This could be mean squared error, or R-squared score. It could be accuracy or precision or recall, or area under the precision recall curve, or cross entropy. There's many metrics for evaluating models depending on your exact task. And I believe Zach lectured on this in a previous lecture. But we don't just have to, we're not limited to using the errors in our predictions as part of our metric or cost function. We could additionally introduce other information into our cost function that we care about. So for instance, if I want to avoid overfitting, then I might want to bias the parameters in my model towards 0. For instance, in a linear regression against 7 different variables, if I think some of them don't actually contribute to making predictions because they're don't appear to be correlated, I could bias the coefficients in those dimensions towards 0. And the way I'll implement that bias in practice is by adding a term to my cost function that introduces a penalty based upon the values of the parameters themselves. So now when I train my model, I'm not just optimizing the mean squared error, but I'm also trying to keep my coefficients as close to 0 as possible. And the impact of this cost, this added cost called the regularization, is controlled by a parameter that I set called alpha. So that's the strength of the regularization. So regularization can help often in the case of very complex models. It's used, for instance, often in neural networks. And it can also help in cases where we have high variance in our data, where our model might be prone to overfitting because it might be because there's so much variance in the data that it's very easy for that variance to get incorporated into the model during training. But regularization won't always make a dramatic improvement in our model, and in fact, sometimes it can negatively impact our model. So here, in fact, the regularized models, Ridge and Lasso, score lower than the ordinary linear regression. But often regularization can help us. So, what is Ridge and Lasso? Ridge and Lasso regression are both linear models, meaning they are linear regression, except, as I said, instead of minimizing mean squared error, we're minimizing the mean squared error plus a regularization term. When that regularization term is the sum of the squared coefficients, as is written here, that's known as ridge regression. When it's the sum of the absolute values of the coefficients, that's known as lasso regression. Now we can see the impact of changing the regularization strength on the performance of the model. For simple linear regression versus ridge, there's virtually no difference over this range of regularization strengths. But for lasso, as we increase the regularization strength, the performance plummets. But generally, we might have different curves here. This is peculiar to this data set, but generally, your score will have some peak across regularization strengths where it performs best. So this regularization strength is a hyperparameter to optimize. And often there will be some value where your model performs best. And often the regularized model may perform even better than the ordinary least squares regressor. So why is lasso so dramatically different from ridge if they're both regularized linear regression? So, crucially, ridge regression biases the coefficients towards 0. As we increase the strength of the regularization, we see some of the coefficients starting to tend towards 0. It's a very slight bias, but you can see that they start to bend towards 0 at the very tail end here. if I increased the values of alpha to go even further, we would see a more dramatic bending. But in the case of ridge, they never actually reach zero. They start to tend towards zero, but they flatten out and only approach zero asymptotically. Lasso regression, on the other hand, at sufficiently high strength, will force coefficients to be zero. So the reason that the lasso regression model does so badly beyond a strength of 0.1 or 1 is because at strength 1, the regularization has actually set all the coefficients in the lasso model to 0. And around 0.1, it's already set most of them to 0. This can be advantageous or not. Lasso, at the end of the day, can resemble feature elimination. Because if I've set a coefficient to 0, then the feature associated with that coefficient no longer has any predictive power in the final model. On the other hand, with lasso, we have to be careful about how strong the regularization is. Even a regularization parameter or strength of 0.1 is pretty extreme in this case for the lasso regressor. While for the ridge regressor, it's hardly making any impact at all. And we would have to go to much higher strengths for the regularization to have much of an impact in ridge regression. So I'm going to conclude this section of lecture here, and in the next video we'll talk about correlations between features and methods such as principal component analysis for constructing subsets of features automatically that alleviates correlation between features and multi-collinearity.